Module 7, Lecture A, Neural Network Basics. By the end of this lecture, you will be able to explain neurons, weights, biases, activations, and layers in plain engineering terms. Network components. Neurons. A neuron in a neural network is a small processing unit that takes several numerical inputs, combines them, and sends an output to the next layer. It does not reason like a person, but it can help detect patterns in data, such as features related to house prices. One neuron is simple, but many connected neurons can model complex relationships. A neuron's output depends on how its inputs are weighted and how easily it activates. Positive weights increase an input's influence, while negative weights reduce it, and the bias shifts the activation threshold. During training, these weights and biases are adjusted so the neuron responds appropriately for its task. After a neuron combines its inputs, weights, and bias, an activation function shapes the result. This lets the network model complex, nonlinear patterns instead of only simple relationships. By combining many activated neurons, neural networks can detect useful features and build powerful prediction models. Python code, neurons. A single neuron can be understood through house features. Each feature is given a weight, like an adjustable engineering knob that controls its influence. The bias shifts the neuron's baseline response, helping determine its final output. The script starts by importing NumPy, a Python library for efficient numerical computing. It will be used to work with arrays and perform the mathematical operations needed for the neuron model, including calculations involving features and weights. We represent a house's scaled features, such as area, bedrooms, and distance, as a NumPy array. This array becomes the neuron's input, organizing the data so it can be used in later calculations. We give each house feature a clear name, such as area, bedrooms, and distance, so the results are easier to understand. These labels let us refer to each feature directly when explaining how it contributes to the neuron's output. Here, the neuron is given 3 weights, 1.2, 0.7, and -0.9. Each weight matches a house feature, such as area, bedrooms, or distance, and controls how strongly that feature affects the output. Changing these weights adjusts the neuron's sensitivity to the inputs and helps model different behaviors. The neuron's bias acts as an adjustable threshold that shifts its baseline response. Setting it to -0.3 lowers the initial output before inputs are applied, helping control how easily the neuron activates in response to signals. This check confirms that the feature and weight arrays have matching shapes, so each feature has a corresponding weight. If they do not match, the code stops with an error before attempting the element-wise multiplication. Each feature is multiplied by its matching weight to measure its contribution to the neuron's input. This scales the feature's influence, producing a set of weighted contributions that show how much each feature affects the neuron's output. The code computes a neuron's raw score by adding together the weighted input contributions, then adding the bias. The bias shifts the neuron's baseline response, acting like an adjustable threshold. This raw score is then ready to pass through an activation function to produce the final output. The sigmoid function converts a raw score into a value between 0 and 1. It does this by using 1 divided by 1 plus the exponential of the negative score. In neural networks, this adds nonlinearity and makes the output easier to interpret as a probability or signal strength. The code gives a brief overview of the neuron's purpose, evaluating signals related to house value. This introduction sets the context before showing the neuron's detailed calculations. The code pairs each feature name with its contribution and prints them together. This gives a concise breakdown of how inputs such as area or bedrooms affect the neuron's output, with values rounded for easier reading. This line shows how the bias affects the neuron's output. It displays the bias rounded to 2 decimal places, making it easier to see how much it shifts the neuron's baseline response before activation. The neuron's raw score is shown before the activation function is applied. It combines the weighted inputs with the bias, giving a clear view of the neuron's initial response before the sigmoid function transforms it. The neuron's numeric output is converted into a simple description. If the activation is at least 0.5, the signal is labeled stronger. Otherwise, it is labeled weaker. This makes the result easier to understand in plain language. The code displays the neuron's final activated output after the sigmoid function, rounded to 2 decimal places. It then labels the signal as stronger if the activation is at least 0.5, or weaker if it is below that threshold, giving a simple engineering interpretation of the result. This script shows how a single neuron turns house features into an output signal. It multiplies each feature, such as area, bedrooms, and distance, by a weight, adds the results with a bias, and then applies a sigmoid activation to produce a value between 0 and 1. The final value is interpreted as a stronger signal if it is above 0.5, and weaker otherwise. Weights. In a neural network, weights control how strongly each input affects a neuron's output. Positive weights encourage activation, negative weights reduce it, and weights near 0 make an input have little influence. In this way, weights act like controls that emphasize or diminish different signals. Weights are the learned connection strengths in a neural network. They usually begin as small, random values, then change as the network sees data and improves its predictions. Important inputs receive stronger weights, while less useful inputs receive weaker ones. In this way, the network learns to turn patterns in the data into meaningful outputs. Weights let neural networks learn complex patterns by shaping information across many connected neurons and layers. Together, millions of weights can help the network detect abstract features, such as patterns in speech or medical images, that would be difficult to define by hand. Their success depends on the quality of the data, the network design, and the training process. Python code, weights. Weights control how strongly inputs influence a simple artificial neuron, much like adjustable gain settings. In this example, NumPy makes the weighted calculation clear and easy to follow. We import NumPy to handle arrays and numerical calculations efficiently. In this script, it supports the computations needed to simulate an artificial neuron, including element-wise multiplication and summation. The setup defines 3 bridge inspection measurements for later analysis: load, crack, and age. Storing these feature names together makes them easy to reference and use in later calculations. Bridge inspection results are stored as scaled feature values in a NumPy array. Each value represents a measurement such as load, cracking, or age. Scaling normalizes the data, making it easier to process and analyze in later calculations. Weights are assigned to each feature to show how strongly it affects the model's output. In this example, the weights for features such as load, crack, and age are 1.5, 2.0, and negative 0.7. Changing these values adjusts how sensitive the model is to each input feature. Before multiplying inputs by weights, The code verifies that both arrays have the same shape. This ensures each input value matches a corresponding weight and prevents calculation errors. The assertion acts as a safeguard by stopping the process if the shapes do not match. Each input is multiplied by its matching weight to measure that feature's contribution. This scales the inputs according to their influence, producing a set of weighted values that together help determine the neuron's output. A bias of -0.4 is used to adjust the neuron's baseline output. This shifts the activation threshold, helping tune how sensitive the neuron is to the input features beyond the weighted inputs alone. The code computes a raw score by adding together each input's weighted contribution, then adding a bias as a baseline adjustment. This produces the value that will be passed to an activation step, where it can be transformed into a more interpretable output. The sigmoid activation function converts a raw score into a value between 0 and 1, so it can be interpreted like a probability. It does this by applying a smooth transformation based on the exponential of the negative score. This makes sigmoid useful for probability-style outputs, especially in binary classification and neural networks. The output summarizes how a neuron combines its inputs. It shows the feature names, input values, weights, and each feature's weighted contribution, with values rounded for readability. It then reports the bias, the raw neuron score formed from the contributions plus the bias, and the sigmoid activated output as a probability-like result. Finally, it identifies the feature with the strongest influence by finding the largest absolute contribution. This script shows a simple artificial neuron that uses 3 scaled bridge inspection measurements: load, crack, and age. Each measurement is multiplied by a weight, then combined with a bias to produce a raw score. A sigmoid activation turns that score into a probability-like output. The printed results show the inputs, weights, contributions, bias, final score, activated output, and which feature had the strongest influence. Hidden layers. Hidden layers are the middle layers of a neural network between the input and output. They transform raw inputs by applying weights, biases, and activation functions, creating useful internal representations. They are called hidden because they are not directly seen as the network's input or final output. In tasks like predicting house prices, these layers help combine features into more meaningful signals for better decisions. Hidden layers let neural networks turn simple inputs into more complex features. Even one hidden layer can model nonlinear patterns, while multiple layers refine information step by step. For example, image networks build from edges to object parts to whole objects, and fraud detection networks use transaction details to separate normal behavior from suspicious activity. This layered structure helps neural networks learn sophisticated patterns from basic data. Hidden layers help neural networks learn complex patterns that go beyond simple linear relationships. Using activation functions, they transform raw inputs into more useful representations for prediction. The number of hidden units must be chosen carefully because too few can miss important patterns, while too many can cause overfitting and inefficiency. Python code. Hidden layers. Hidden layers transform engineering measurements by having neurons combine weighted signals. Activation functions then add flexible, curved behavior to help the model represent more complex patterns. We begin by importing NumPy, a key Python library for numerical computing. It helps us work efficiently with arrays and matrices, which are central to neural networks and many machine learning tasks. NumPy makes large data and complex calculations easier to handle. The code sets NumPy's print options, so numerical output is consistent and easy to read. It shows values to 3 decimal places and avoids scientific notation for small numbers, which makes demonstrations clearer. The input features for a small building site are defined as one row of data with 3 values: area in square meters, number of bedrooms, and building age in years. This structured input gives the model the information it needs to make a prediction about the site. The code creates a scaled set of input feature values 1.2, 0.6, and 0.36. Scaling keeps the inputs in comparable ranges, which helps stabilize neural network training and can improve performance. Before multiplying matrices, the code confirms that the scaled input has 1 row and 3 columns. This check ensures it matches the weight matrix and helps prevent shape mismatch errors. This step defines the weights connecting the input features to the hidden neurons. The weights are stored in a 2-dimensional array, with rows for input features and columns for the 4 hidden neurons. These weights let each neuron combine information from all inputs, helping the network learn patterns in the data. Biases are added to the hidden layer, with 1 bias for each of the 4 hidden neurons. These values shift each neuron's activation threshold, giving the network more flexibility in how it responds to inputs. This helps the model learn more complex patterns in the data. The ReLU function applies the rectified linear unit activation to an array of numbers. It compares each value with 0 and returns the larger one, so positive values stay the same while negative values become 0. The hidden layer first creates raw signals by multiplying the scaled input features by the hidden layer weights and adding the neuron biases. These raw signals are then passed through the ReLU function, which keeps positive values and turns negative values into 0. This adds nonlinearity and produces the activated outputs of the hidden layer for the next computation. The output layer converts the hidden features into the model's final prediction. It uses 1 weight for each of the 4 hidden neurons, along with a single bias value. The weights connect the hidden layer to the output, while the bias shifts the result so the model can adjust its prediction independently of the inputs. Before making the final prediction, the code checks that the hidden layer output has the expected shape, with 4 features. This confirms the data is structured correctly for the next neural network step and helps prevent matrix operation errors. The model makes its prediction by multiplying the hidden layer's output by the output layer's weights. This combines the learned features into 1 output value, then adds a bias to adjust the final prediction. A direct linear model is set up with 3 feature weights and a single bias value. The prediction is then computed by multiplying the scaled input features by the weights and adding the bias. This gives a simple linear baseline that can be compared with the more complex neural network model. The example shows how a neural network processes building features such as area, bedrooms, and age to make a prediction. It first computes raw hidden layer signals, then applies the ReLU activation to create learned intermediate features. The final network prediction is compared with a simpler direct linear model, highlighting that hidden layers help the model capture more complex patterns in the data. This script shows how a simple neural network uses 1 hidden layer to turn scaled input features into a prediction. The hidden layer has 4 neurons that combine the inputs with weights and biases. Then apply ReLU activation to create learned intermediate features. These features are passed to an output layer for the final prediction, which is compared with a direct linear model. The results show the hidden layer signals and illustrate how hidden layers add complexity that can improve prediction. Forward pass, matrix inputs. During a forward pass, input data is stored in a matrix, with each row representing one example and each column representing a feature. This format lets a neural network process many examples at once, whether predicting rent from apartment features or classifying emails from word counts. The network then transforms these inputs through its layers to produce predictions efficiently. Matrices help keep neural network inputs aligned with the expected dimensions. Each row should contain one example, and its feature values must match the first layer's input connections in the correct order. Because the network only processes numbers, pre-processing such as scaling and handling missing values is important. Once the data is organized, NumPy can apply weights and biases efficiently across the whole batch. Matrix inputs show why neural networks work well with modern data. Batches of examples can be processed in parallel, using the same weights and biases, which helps models scale efficiently. Python code, matrix inputs. Matrix inputs organize engineering observations in a structured way. Each row represents one apartment example, and each column contains the same type of numerical feature measurement across all examples. We begin by importing NumPy, a key Python library for numerical computing. It helps us work efficiently with arrays and matrices, which are needed to represent data and model parameters in the script. We define a list of feature names to label each apartment attribute, such as area, bedrooms, and distance. These labels make the data easier to understand by showing what each column in the matrix represents. A NumPy matrix can represent a batch of apartment data, with each row describing one apartment and each column storing a feature such as square footage, number of bedrooms, or distance. This structure makes it easy to process and analyze multiple apartments at the same time. The first layer of the neural network has two neurons, and its weights are stored in a NumPy array. Each row represents an input feature, such as area, bedrooms, or distance, while each column represents one neuron. These weight values define how strongly each feature connects to each neuron and are used to compute the neuron's inputs. The first layer uses two bias values, one for each neuron. These biases adjust each neuron's input before the activation function is applied, helping shift the activation threshold so the model can learn more effectively. Before multiplying matrices, confirm their dimensions are compatible. The input matrix must have the same number of columns as the weight matrix has rows, so each feature has a matching weight. If not, the multiplication cannot be performed and will produce an error. For the whole batch, the network computes the first layer's neuron inputs by multiplying the input data by the layer's weights. It then adds the bias values to each result, shifting the inputs before the activation function is applied. This prepares the data for the next stage of processing. The ReLU activation function is applied to the first layer's output matrix. It keeps positive values and changes negative values to 0. Adding the nonlinearity needed for the network to learn complex patterns. The result is the activated output of the first layer's neurons. The output layer weights determine how the hidden neuron activations are combined to produce the network's final prediction. Here, the weights are stored in a NumPy array with values of 900 and 500 used to scale the hidden layer activations before they are summed to predict rent. The code creates an output bias with a value of 700, giving rent predictions a realistic starting point. This constant shifts the model's final output before other calculations adjust it, which is a common way to set a useful baseline in a neural network. Before computing the output layer, check that the first layer's activation matrix and the second layer's weight matrix have compatible dimensions. The activations must align with the weights, so each first layer output can be combined correctly. This ensures the final predictions can be calculated accurately. To predict rent, the model combines the first layer's outputs with the second layer's weights, then adds a bias term. This bias represents a baseline rent level and shifts the result to account for fixed or starting values. The final output gives the predicted rent for each apartment in the input data. The output checks the model's data flow by showing the input matrix shape, the first layer's output shape, and the final prediction shape. It also prints the feature order, so each input column is clear. Finally, it displays the predicted rents rounded to 2 decimal places, giving a quick summary of the model's results. This script uses a simple feed-forward neural network to predict apartment rents from features such as area, bedrooms, and distance. The data is passed through a weighted first layer, filtered with a ReLU activation that keeps positive values, and then processed by an output layer to produce rent predictions. When run, it shows the shapes of the main matrices, the feature names, and the predicted rents rounded to 2 decimal places, illustrating the basic flow of matrix operations and activation functions in a neural network. Array activations. In a NumPy neural network, activations are the arrays produced when a layer combines its inputs with weights and biases, then applies an activation function. They represent what the network has learned about the data at that stage. Each activation array becomes the input to the next layer, creating the sequence of transformations known as the forward pass. Activation functions make neural networks more flexible by letting layers learn nonlinear patterns. Without them, multiple layers would behave like a single linear transformation. By reshaping raw outputs, such as reducing negative values or compressing large ones, activations turn calculations into useful signals for the next layers. NumPy arrays make neural network forward passes efficient by processing many neurons and data examples at the same time. Each layer takes an array, applies an activation function, and sends the result to the next layer. Keeping array shapes consistent helps the network move smoothly from input data to final predictions. Python code. Array activations. Use small engineering arrays to demonstrate activations, where each layer turns measurements into signals. NumPy makes this efficient by processing many examples at the same time. We begin by importing NumPy, a library available in Google Colab for efficient numerical computing. It helps us work with arrays and matrices, which are central to the calculations in this script. To make NumPy output easier to read, set the display options to show numbers with 3 decimal places and avoid scientific notation for small values. This keeps numerical results in a clear standard decimal format, which is especially helpful for beginners. We use a NumPy array to store 3 building examples, each described by 3 scaled features. Organizing the data this way makes it easy to process all examples together efficiently using NumPy. Before multiplying matrices, the code verifies that each example has the expected 3 features. It checks the feature array's second dimension and stops if the count is wrong. This simple validation helps prevent errors in the matrix operations that follow. The first layer's weights are stored as a NumPy array with 3 rows and 4 columns. This represents connections from 3 input features to 4 hidden layer neurons. Each value is a connection weight that helps transform the inputs into signals the neurons can process. The code defines 4 bias values for the hidden layer. Each bias is added to a neuron's weighted input sum, shifting its output and giving each neuron its own baseline activation. This helps the model learn more complex patterns. The ReLU function processes an array by keeping positive values unchanged and replacing negative values with 0. This lets only positive signals pass through, which helps neural networks introduce nonlinearity. The hidden layer first computes raw scores by combining the input features with the layer's weights and biases. These scores are then passed through the ReLU function, which keeps positive values and suppresses negative ones. The result is a set of hidden activations that carry the process signals forward to the next layer. The output layer uses 4 weights, one for each hidden neuron, arranged as a column vector to match the hidden layer activations. It also includes a single bias value, which shifts the final output and helps the model account for a consistent offset in the data. The hidden layer activations are converted into final predictions by multiplying them with the second layer's weights and adding the second layer's bias. This produces raw output scores for each example, which are then reshaped into a one-dimensional form so they are ready for further use. This section checks how data moves through the model by printing the shapes of the input features, hidden activations, and final predictions. It also displays the hidden activations after the first layer and ReLU function, then shows the predicted relative demand produced by the model. This script shows a simple 2-layer neural network built with NumPy to process features for 3 buildings. The first layer transforms the input features into hidden scores. Then a ReLU activation keeps only the positive values. A second layer uses those activations to produce final predictions for relative building demand. The output displays the data shapes, hidden activations, and predictions, illustrating the basic flow of transformations in a neural network. Output prediction. At the end of the forward pass, the network turns its processed information into a prediction. The final layer outputs an array whose shape depends on the task. A single value for something like price prediction, a probability for binary classification such as spam detection, or multiple values for multi-class classification. Each output value is interpreted according to the categories or target defined by the engineer. When using NumPy arrays for prediction, the shape and organization of the data are just as important as the values. A network can process one example or a whole batch, producing matching predictions for each input in the same forward pass. This makes batch processing efficient, but the final prediction array must stay correctly aligned with the original inputs. To interpret a neural network's final output, consider both the activation function and the type of decision being made. Regression outputs are usually direct numeric predictions, while binary classification often gives a confidence score between 0 and 1. Multi-class models spread scores across categories, with the highest score usually indicating the predicted class. These outputs still need context, such as a decision threshold for fraud risk or clinical judgment for medical estimates. Python code output prediction. This example shows how a model can predict bridge maintenance risk. NumPy arrays move batches of data through the layers, and the model's outputs are used to support engineering decisions. We begin by importing NumPy, a key Python library for efficient numerical computing. It helps manage array-based bridge inspection data and supports the matrix operations needed for neural network calculations. 3 bridge inspection examples are stored in a NumPy array, with each row representing one bridge, and each column representing an inspection metric. This structure lets the data be processed together as a batch through later neural network layers. The code verifies that the bridge inspection input data has the expected 3x3 shape. This check helps confirm the data is prepared correctly before it is used by the neural network. If the shape is different, it signals a possible problem in data loading or preparation. The first layer's weights are stored in a 3x4 array, linking 3 input features to 4 hidden neurons. Each value sets the strength of one connection and helps determine how the network transforms input data. These initial weights, whether positive, negative, or 0, influence the network's predictions. The hidden layer uses 4 bias values, one for each neuron. These biases are added to the weighted input before the activation function, helping the network adjust its outputs more flexibly. The initial values are 0.1, negative 0.2, 0.05, and 0. The output layer uses 4 weights, 1.2, negative 0.7, 0.9, and 0.4, to control how strongly each hidden node affects the final prediction. It also uses a bias of negative 0.1, which shifts the output independently of the inputs and helps the model fit the data more flexibly. Check that each matrix dimension lines up before passing data through the network. The input must be compatible with the first layer's weights, and the first layer's output must be compatible with the second layer's weights. These checks ensure each multiplication is valid and data flows correctly between layers. The hidden layer first combines the input data with its weights and biases to produce raw signals. These signals are then passed through the ReLU activation function, which turns negative values into 0 and leaves positive values unchanged. This adds nonlinearity, helping the model learn more complex patterns. The model first combines the hidden layer outputs with the output layer weights and bias to produce a raw output signal. It then applies the sigmoid function to convert that signal into a value between 0 and 1, giving a risk score for each bridge inspection example. This code turns risk probabilities into clear decisions using NumPy's where function. Scores at or above 0.5 are labeled inspect, meaning the bridge needs inspection, while lower scores are labeled monitor. This makes the risk results easier to act on. The output first checks the dimensions of the input data and the resulting risk scores. It then shows the risk values rounded for readability and assigns each bridge a decision to inspect or monitor based on whether its risk reaches the threshold of 0.5. Each output row matches the corresponding input bridge, making the results easy to interpret. This script uses a simple 2-layer neural network to estimate maintenance risk for 3 bridges from inspection data. A hidden layer applies a rectified linear activation, and the output layer uses a sigmoid function to turn the results into risk probabilities. Scores above 0.5 indicate that a bridge should be inspected, while lower scores suggest continued monitoring. The script reports the input and output shapes, the rounded risk scores, and a maintenance decision for each bridge. Model flexibility, nonlinear decision boundaries. A decision boundary is how a model separates predicted classes. Linear models such as logistic regression use rigid, straight, or flat boundaries, which work well for simple patterns. Many real-world tasks, such as diagnosis or fraud detection, involve more complex interactions. Neural networks can handle these patterns better because hidden layers and nonlinear activations let them form more flexible boundaries. Neural networks can form nonlinear decision boundaries by building intermediate representations before making a prediction. Different neurons detect partial patterns, and later layers combine them to make more refined decisions, such as using curves and loops to tell similar handwritten digits apart. This makes neural networks flexible function approximators that can capture complex patterns beyond what simple linear models can learn without heavy feature engineering. Neural networks can model complex nonlinear relationships that simpler linear or logistic models may miss. This makes them useful for data with subtle feature interactions, such as speech signals or customer behavior. However, their flexibility can lead to overfitting if the model is too large or not properly controlled. For simpler patterns or smaller datasets, linear and logistic models are often easier to explain and faster to train. Python code, nonlinear decision boundaries. This section compares straight and curved decision boundaries using synthetic engineering inspection data. It shows how neural networks combine simple, nonlinear neuron responses to model more flexible boundaries than a straight line. We begin by importing NumPy for efficient numerical work with arrays and matrices. We also import Matplotlib's plotting tools so the script can visualize data points and decision boundaries. We set NumPy's random seed to 7, so the same random numbers are produced each time the code runs. This makes experiments and debugging reproducible. We create a grid of inspection points by generating evenly spaced horizontal and vertical values from -3 to 3. Each axis uses 160 points, forming the coordinate grid needed to plot decision boundaries later. To plot decision boundaries, we first use NumPy's meshGrid function to create a grid of x and y values across the chosen range. These grid values are then flattened and combined into coordinate pairs, giving a set of points that can be evaluated to visualize the decision regions. Before running the model calculations, the code validates the point grid. It checks that each point has 2 coordinates, confirming a 2-dimensional setup, and that the grid contains more than 100 points. This helps ensure the input is suitable for analysis and prevents later computation errors. A simple linear classifier scores each point by adding its x and y coordinates and subtracting 0.2. Points with a positive score are assigned to class 1 and the rest to class 0. Reshaping these class labels to match the grid makes it possible to visualize the resulting straight decision boundary. The sigmoid function is a common neural network activation function that transforms an input into a value between 0 and 1. It does this using 1 divided by 1 plus the exponential of the negative input. Because its output fits a probability range and adds nonlinearity, it is useful for binary classification and for helping neural networks learn more complex patterns. We define the first layer of a small neural network using a set of weights and biases. 4 hidden neurons are arranged so that some respond mainly to the first input and others to the second, with positive and negative weights creating different linear responses. Each neuron also has a negative bias, which shifts when it becomes active. Together, these settings help the network capture nonlinear patterns in the data. The network combines the hidden neuron outputs using 4 equal weights, each set to 1, and a bias of -1.35. These values produce the final nonlinear score and help shift the decision boundary for classification. The network first computes the hidden layer by combining the grid points with the first weights and biases, then applying the sigmoid function to produce neuron activations. It then combines those activations with a second set of weights and a bias to get a prediction score for each point. Finally, Points with scores greater than 0 are assigned to one class, and the results are reshaped into a binary map showing the decision boundary. We generate sample inspection points in polar coordinates by choosing random directions and distances from the center. The angles are uniformly spread around the full circle, while the radii follow a normal distribution centered near 1.8, creating a ring-like pattern. These polar points can then be converted to Cartesian coordinates for further analysis. To convert polar coordinates to Cartesian coordinates, find the horizontal position by multiplying the radius by the cosine of the angle, and the vertical position by multiplying the radius by the sine of the angle. These two values are then paired together to give each sample point its Cartesian coordinates. Each sample point is classified by its distance from the origin, found using the Pythagorean theorem from its x and y coordinates. Points farther than 1.55 are labeled 1, while the rest are labeled 0. This creates two classes separated by a ring-shaped decision boundary. The code summarizes the decision boundaries used in the analysis. It contrasts a linear model, which separates data with one straight line, with a neural network, which can form multiple curved regions for more flexible separation. It also reports how many grid points were evaluated for visualization and how many hidden neurons the network uses, indicating its capacity to model nonlinear patterns. To compare decision boundaries, we set up one figure with two side-by-side plots using Matplotlib. The layout has one row and two columns, with a size large enough for clear viewing. This lets us show the linear model and neural network boundaries together for easy comparison. The plot shows the linear model's decision boundary as shaded regions, making it clear how the model classifies different areas of the sensor offset grid. The inspection points are overlaid and colored by their labels, with black edges to keep them easy to distinguish. The subplot is titled Linear Model, and the x-axis is labeled Sensor Offset Inches to clarify what the visualization represents. The plot shows the neural network's decision boundary by shading regions according to the class the model predicts. Sample inspection points are then placed on top and colored by their true labels, with dark edges to make them easier to see. The subplot is titled Tiny Neural Network, and the x-axis is labeled Sensor Offset Inches. To make the plots easy to compare, each axis is formatted the same way. The y-axis is labeled as vibration change in millimeters per second. The aspect ratio is kept equal to avoid distortion, and a lightly transparent grid is added to support visual interpretation without cluttering the plot. The tight layout function adjusts subplot spacing so the figure elements fit cleanly without overlapping, which is especially helpful for multiple plots. Then the show function displays the finished visualization, including the decision boundaries and sample points created earlier. This script compares linear and nonlinear decision boundaries using synthetic, ring-shaped data. A simple linear classifier creates a straight boundary, while a small neural network with sigmoid activations produces a curved, more flexible boundary. By plotting the two results side by side with labeled sample points, it shows that neural networks can capture more complex class patterns than a linear model. Nonlinear decision boundaries. A decision boundary is how a model separates predicted classes. Linear models, including logistic regression without extra feature engineering, use a straight or flat boundary. So they work best when the data can be split in a simple way. This can be effective for problems with one dominant trend, but many real-world tasks involve complex interactions that a linear boundary may not capture well. Neural networks use layers of neurons and activation functions to create nonlinear decision boundaries. This lets them model complex patterns, curve around data clusters, and capture feature interactions without manual rules. As a result, they are well suited for tasks with intricate data, such as image recognition and fraud detection. Nonlinear decision boundaries can model complex patterns, but they must be tuned carefully. A model that is too simple may miss important structure, while one that is too complex may learn noise instead of real patterns. Neural networks are harder to interpret and train than linear models, but they can perform better on layered data such as speech or images. The main question is whether their extra flexibility improves accuracy on new data. Python code. Nonlinear decision boundaries. This section compares straight and curved decision boundaries using tiny synthetic data to keep runtime predictable. It also shows how NumPy can be used to build simple models without relying on machine learning libraries. We import NumPy to efficiently create and work with synthetic data and use Matplotlib's plotting tools to visualize the results. These libraries let us plot data points and decision boundaries so we can compare linear and nonlinear models. To make random results repeatable, set a fixed seed in NumPy's random number generator. Using the same seed, such as 7, produces the same sequence each time the code runs, which helps with debugging and checking experimental results. The process creates 160 points for each circular zone. It assigns each point a random angle between 0 and 2 pi, using the initialized random number generator. This spreads the points around the circle to model a circular risk zone. Random radii are drawn from a normal distribution centered near 1, with a small amount of variation, to create points clustered around a circle. Each point's position is then found using its radius with the cosine and sine of its angle, placing the points in a circular pattern that represents an inner risk zone in 2 dimensions. Random outer circle radii are generated from a normal distribution centered at 2, with a small standard deviation to vary the circle size. These radii are converted into Cartesian points by using the cosine and sine of the angles for the x and y coordinates, then combined into a 2-dimensional set of outer circle points. The inner and outer circle points are combined into one dataset, with each row representing a 2-dimensional point. Labels are then created to identify the groups, using 0 for the inner circle and 1 for the outer circle. These labels are matched to the combined points, preparing the data for analysis or modeling. The code first checks that the feature data has the expected size, 2 rows for each point and 2 features per row. It then checks that the labels include 1 entry for every data point. These checks help confirm the dataset is consistent before training or evaluating a model. Each data point is given a linear score based on its 2 features and a small constant offset, which defines a straight-line decision boundary. The model then checks whether the score is above 0 to assign one of 2 classes. The result is a binary set of predictions, with each value indicating the predicted class for a data point. Each point is scored by using its squared distance from the origin, then subtracting 2.25. Points with a positive score are classified as 1, and the rest as 0. This creates a curved decision boundary that can better match the shape of the data clusters. We evaluate each model by measuring accuracy, the proportion of predictions that match the true labels. This is done for both the linear and nonlinear models, showing how well each decision boundary classifies the data points. We first check the dataset shape to confirm how many data points and features it contains. Then we compare the accuracy of a linear model with a straight decision boundary to a nonlinear model with a curved boundary. The main takeaway is that nonlinear boundaries can better wrap around clusters, making them more flexible for capturing complex patterns. To prepare a plotting grid, we create a sequence of values from -2.7 to +2.7, using 220 points to set the range and resolution. This sequence is then turned into a two-dimensional mesh grid of coordinates. The grid lets us evaluate and visualize decision boundaries, showing how models separate data across the space. Decision boundaries are evaluated across a grid of points to compare how models separate data. A linear boundary is computed from a weighted combination of the coordinates, producing a straight dividing line. A nonlinear boundary is computed from the squared coordinates, producing a circular boundary similar to what a neural network might learn. We use matplotlib to create a figure with two side-by-side panels, so two plots can be compared within the same view. A 10 by 4 inch figure gives each panel enough space to be clear. This layout is useful for visual comparisons, such as showing different decision boundaries on the same dataset. The first panel shows the dataset as a scatter plot, with each point placed by its coordinates and colored by its label. A black contour line is added where the linear model changes class, marking the decision boundary. The panel is titled to emphasize that the linear model creates a straight split, and the axes use an equal scale, so distances are represented accurately. This section shows how to plot a curved decision boundary. The data points are displayed on the second subplot using their coordinates, with colors indicating their labels. A black contour line is then added where the nonlinear grid values equal 0, marking the boundary between classes. The plot is titled as a neural network-like curved split, and an equal aspect ratio keeps the axes scaled accurately. The code adds clear labels to each plot axis so the data is easier to interpret. It labels the horizontal axis as the sensor A reading and the vertical axis as the sensor B reading, showing that each point compares measurements from the two sensors. The tight layout command automatically adjusts spacing so subplots fit neatly within the figure without overlapping. This is especially helpful when a figure contains multiple plots. The show command then displays the finished figure on the screen, completing the visualization process. This script compares linear and nonlinear decision boundaries on synthetic circular data. A straight line model only separates the risk zones moderately well because the pattern is curved. A nonlinear model uses a circular boundary that matches the data more closely, leading to higher accuracy. The key point is that nonlinear boundaries can capture complex data patterns that linear models may miss. Nonlinear decision boundaries. A decision boundary is how a model separates predicted classes. Linear models, including logistic regression without feature transformations, use simple boundaries such as lines or planes, which work well for simple patterns. For more complex real-world data, neural networks can transform inputs through hidden layers, allowing the boundary to fit more complicated shapes. Neural networks can learn nonlinear decision boundaries by using hidden layer neurons to detect patterns and combine them into complex shapes. This lets them handle relationships that are not captured by simple straight-line models. For example, they can recognize image features such as wheels or frames, or predict customer purchases from interactions among income, browsing history, and other factors. Neural networks give engineers more flexibility than linear models, but they also require more careful evaluation. Linear models are easier to interpret and can work well when patterns are simple, while neural networks are better at capturing complex feature interactions and changing decision boundaries. This makes them useful for tasks like speech recognition, where inputs vary by accent and speed. However, because they can also memorize quirks in the training data, strong validation is essential to ensure they generalize to new examples. Python code, nonlinear decision boundaries. This section compares straight and curved decision boundaries in classification. It highlights that neural networks can bend classification regions, allowing them to model more flexible patterns. The example demonstrates this idea using only NumPy. We import NumPy for efficient numerical work with arrays and calculations, and Matplotlib's plotting tools to visualize data and decision boundaries. Together, these libraries provide the basic tools needed for analysis and graphics in the script. We create a two-dimensional grid by generating evenly spaced values from -3 to 3 along both axes. A mesh grid then turns these values into coordinate matrices for every point in the space. This grid lets us evaluate functions across the plane, which is useful for visualizing decision boundaries. The grid coordinates are prepared as model input by flattening the x and y values and combining them into coordinate pairs. Each pair represents one point in two-dimensional space with exactly two features, so the resulting array has the correct shape for further processing. Each point is assigned a linear score by adding its x and y coordinates and subtracting 0.2. The point is then classified based on whether that score is above 0. This creates a simple linear decision boundary that separates the feature space into two classes. We define two hidden neurons by choosing their center positions in the feature space. A width value then controls how far each neuron's influence spreads, shaping how strongly it responds to nearby input points. The method measures how far each data point is from each cluster center by aligning their dimensions and computing squared distances. These distances are then passed through an exponential transformation scaled by the width, producing hidden activations. The activations are strongest near a center and decrease with distance, representing each center's influence on nearby points. The network makes nonlinear predictions by combining the outputs of two hidden neurons and adjusting the result with a threshold. If the final score is greater than 0, the point is assigned to one class. Otherwise, it is assigned to the other. This lets the model create more complex decision boundaries from the hidden neuron activations. The predictions are reshaped from a flat list back into the original grid for both the linear model and the network model. This matches each predicted class to its x and y grid point, so the decision boundaries can be plotted clearly on the two-dimensional plane. The code summarizes how each model separates the data. The linear model creates one straight decision boundary, while the neural network forms two curved, high-risk, or uncertain regions. Its hidden neurons act as pattern detectors that capture more complex structure in the data. We create a figure with two side-by-side plots using Matplotlib's subplot tools. The figure is sized to fit both plots clearly, making it easy to compare the decision boundaries of a linear model and a neural network in one view. The first subplot shows the linear decision boundary. A filled contour separates the two classes using the linear model's grid values, while a contour line marks where the model score is 0. The plot is labeled with the title Linear Boundary and the x-axis as Feature 1. We visualize the neural network's nonlinear decision boundary with a filled contour plot that shows which regions are assigned to each class. A contour line marks where the network score is 0, indicating the transition between classes. The plot is titled to identify the nonlinear neural boundary, and the x-axis is labeled as Feature 1 for clarity. To make the plots easy to compare, each axis is formatted the same way. The y-axis is labeled Feature 2. The aspect ratio is set equal so distances are not distorted, and a lightly transparent grid is added to improve readability without cluttering the view. To finish the visualization, the tight layout function adjusts subplot spacing so the plots do not overlap. Then the show function displays the result, making it easy to compare the linear and nonlinear decision boundaries side by side. This script compares linear and nonlinear decision boundaries. A simple linear model separates points with one straight line, while a small neural network with two hidden neurons creates a more flexible, curved boundary. The side-by-side visualization shows how neural networks can capture more complex patterns than a rigid linear classifier. In this lecture, you learned to explain neurons, weights, biases, activations, and layers in plain engineering terms. Implement forward prediction for a small neural network using NumPy arrays, and compare neural network flexibility with linear and logistic models. In the next lecture, Lecture B, we will go over training networks. Thank you for your attention. See you all in the next lecture.